In this presentation, we're going to look at combinations of normal random variables. So let x and y be two independent random variables following normal distributions, n with mu equal 15 and variance equals 5 squared, 25, and the y which with mu equal to 12 and variance equals 10 squared, 100. And what we're going to do here is define a linear combination of x and y, which is z or z, I say z, equals x minus y plus 5. Determine the distribution of y and its mean and variance, and calculate the probability that a sample of size 5 drawn from z has a mean greater than 10 and a standard deviation greater than 20. Okay, that second part's quite tricky. It's got a lot going on in it. Okay, so first off, let's start off with x and y. Okay, just specify them, just properly state them. And what we have to do here is determine the distribution of x and y. So essentially what we have to do is specify it in the same way as we have done here. So what we have to do is calculate the mean and the variance of z, or just state it really. Okay, so the mean of z is actually just the mean of x plus the mean of y minus the mean of y, sorry, I should put minus there, plus 5. So it's 15 minus 12 plus 5, so it is 8. So the expected value of z, the mean, is 8. Okay, now, and what we're going to do is calculate the variance of z. Okay, so in this case what we would do is just add the variances. Now, so I made a mistake there where I should have a minus sign in there when I had a plus, but this actually is a plus. That's not a mistake. So you add the variances there. Variance of x plus the variance of y. Now, really, we could have a variance of 5 just to sort of round things off, but that's just going to be 0. There's no variance there, essentially. Well, actually, it doesn't vary. The variance is 0, so we don't really need it. It's superfluous. So variance of x plus the variance of y. We don't really need to say anything about 5 because the variance is just 0. So there we have it there, 25 plus 100, and that is equal to 125. The square root of that is 11.18. Okay, so that's the answer there. Z is normally distributed random variable with mean of 8 and a variance of 11.18 squared. Okay, or you could write it in as 125. My pen keeps slipping for some reason. I'm going to just take a pause for a second. Okay, I'm back from the second part here. Okay, calculate the probability that a sample of size 5 drawn from Z has a mean of greater than 10 and a standard deviation greater than 20. So let's just go down here. So this is the underlying distribution Z, and it's normally distributed with a mean of 8 and a variance of 11.18 squared, which is 125. Now, what I have to put in here is the sampling distribution, and I have to write this in. So this is the sampling distribution of the mean of Z for a sample size of 5. I should write that in also. And that is normally distributed. The mean doesn't change, but the variance will. So for a sampling distribution, it's the variance divided by the sample size. Okay, and in this case, it's 125 divided by 5. Okay, we can simplify that as 25, and we can simplify that again as 5 squared. Okay, so what we're interested in here is the probability of the mean being greater than 10. So this is a straightforward normal calculation here, and I've had to sort of fix some mistakes there on the fly, but this is the standard normal distribution Z. So just to be clear, this is going back to basics. This is Z score stuff. Okay, it's not related to this at all. Okay, so it's a little bit, we're just sort of using standard notation there, but it's a little bit confusing when we're also calling a different variable Z. So this is just Z score stuff. So I'd almost put it in a sort of separate box there as a separate calculation there and just sort of say Z score. But this is going back to where we need to be. This is equal to 1 minus the phi function, the cumulative distribution function of 0.4. Little bit, that's either using statistical tables or programming languages like R. Should be able to figure that out. And we should get a probability there of 0.3446. Okay, so the variance now is the sample variance being greater than 20. Okay, so this is how we would work it out here. Okay, this is what we have to work with here. N minus 1 times S squared all over chi squared. Okay, sorry, sigma squared. That should be sigma. I'm making loads of mistakes in this. So the sample variance here is going to be 20. And that means that 20 times 20 gives us S squared of 4,000. Okay. N minus 1 is 5 minus 1, which is 4. And sigma squared is 125. Okay. So essentially what we have to do is calculate the probability of chi squared, or this chi squared value being greater than 12.8. Okay. Degrees of freedom equal to 4. Okay. So this is using the chi-square tables. Okay, this is a chi-squared random variable with degrees of freedom n minus 1. So this is where we should end up. Okay, 4 times 4,000 over 125 gives us 12.8. That should give us a probability of 0.0124. Now again, using either statistical tables there, which is probably unlikely, or using a programming language. So these are independent events. So essentially what we have to do there is just multiply out the probabilities of the two events. 0.3446 times 0.0124, and that gives us an answer there of 0.0043. Okay, so that's it there. Apologize for those mistakes. That's sigma there, sigma squared there. The key thing there really is this stuff here, knowing this stuff here. Chi-squared, sample variances, sampling distribution of sample variances, and so on.